Hello, everybody. It's a great pleasure to be part of ISTA, and our talk is about application of formal methods in quality engineering. I'm Hovhannes Bolibekyan, and the talk is co-authored with Artur, Aghabekyan, and we are both from VMware. So nowadays we are living in computer society, in electronic society, and computers are everywhere in our life. We are using watches, we are using faxes, phones, lots of mobile devices and computers, and everywhere there is a software, embedded software, different kinds of software we are dealing with. And per statistics, an average home in developed country has one PC and lots of embedded devices. It's okay to use when we talk about the software. We always think about the quality of the software, how it interacts with us, with the endpoint user, how reliable it is, how how robust it is, and it is okay if sometimes something doesn't work, if your mobile hangs on or your fridge doesn't work. It's okay unless you are very angry or you are not very hungry. If you're if all the products in your fridge are spoiled. But the quality of software system is very important when we deal with critical systems, where when we deal with nuclear or industrial plants, when it is aircrafts or trains, the software systems reliability is very important. And so we can talk about the quality of consider quality of computational system as quality of life. All these systems, different systems, are being verified, being tested with lots of engineers, lots of development staff, lots of quality engineers, and nevertheless, the history reveals, gave us some lessons. It is problems that were detected in the industry after the products were released into the market. It is, as an example, I just mentioned some of the well-known issues. It is a Pentium bug that was discovered in chip. It was related to floating point division, and it brought to the loss of revenue in $475 million. Area failure was caused rocket explosion immediately after the start, and revenue loss is very bad, but it is much bad, and it is much more important when we deal with human lives. And the last example is a software failure that caused incorrect dosage of X-ray, brought to loss of human life. So what is a verification? When we talk about verification, it is we have to say that it is the process of ensuring system correctness, and system is correct when it does what it is supposed to do, and it is as an example, I will bring the following example. So if you want to if you request statement from your online banking system. It should bring all your statement without change of your account balance. So if the request of a balance statement changed your balance account balance, it is not definitely, it definitely doesn't do what it is supposed to do. We also need to think about robustness during verification process. And talking about robustness, we mean that in any case, software cannot do what it is supposed to do. It behaves in some reasonable way. It doesn't cause failure of the system. And during software development lifecycle, almost 70% of time is being spent on verification. It is not just testing, it is verification, and it is validation. So what kind of verification we are talking about? So we can divide verification into two large groups. It is design verification and implementation testing. During design verification, we deal with design or coding errors. It is every software when software products are developed. First of all, it is we have a list of specifications, unless it is not being developed in some garage, something like a startup, when just an idea came into your mind and you try to quickly implement it. But it was also mentioned by Bjorn today that in a during the specification phase, we need to involve not only development stuff. On the specification phase, it is well known that quality engineers are being involved in the process, and it is also endpoint users are being involved in specification phase. So what is the specification? How we deal with the specification? When we develop something, we just write it in natural language. It is might be English, Bulgarian, any language that is understandable for everybody participating in the team. And sometimes, quite often, it is used. We use some diagrams, some specific tools to easily grasp the idea. During implementation testing, we deal with translation of specification into some high-level language. It is we just code already given idea, and also we deal on implementation testing phase. We deal with fabrication defects when we are talking about manufacturing hardware. And during traditional design verification, it comes into several steps that we are going through. It is testing and simulation, and what we are testing, how we detect the problems in the software. We are going through different review processes, going several times forward and backward, and trying to find out what was wrong in specifications, polish it out, then come back and do changes in the code that was based on the specifications. But when we talk about critical safety systems, it is inadequate, because we cannot judge with, we cannot deal those systems in such a manner. Even famous quotation of Dijkstra was about finding bugs. He mentioned that testing can reveal the bugs in the product, but it is not possible to prove that there is no bug in the software after testing, when the testing is finished. But another question, when we are when we can say that the testing process is done. So it is time to deliver to the market, or we provided enough coverage of the functionality, or we worked on different input vectors, input data, and we considered all of them. It is really hard problem to decide when to stop testing process, and during traditional testing, it is we go through simulation and run either model or system itself on different input data, and it is we try to detect behavioral issues in the product. Okay. What are the test vectors, and trying to give an input information, we have to think about test vectors, and what is a test vector, what is a right test vector. Dealing with especially dealing with hardware testing, it is very hard to consider all of input vectors. Even the best automation sometimes cannot cover all possible inputs from the all possible inputs, and so sometimes we say, okay, it is 90% of possible inputs are tested, and the software most probably will be okay with behavior will be correct, but we cannot have guarantees that the software will function properly in case of then the rest 10% of input vectors. So we can select corner cases when the boundary conditions, when the system can fail, and try to test these software or embedded system on those vectors. But that also doesn't guarantee fully functionality of the system. It is a computational hard problem to generate a big number of vectors. It is computational, it is logically difficult to understand which are the right vectors to use as an input. We can use golden models, but golden models, it is again tricky question whether the golden model is selected in the right direction or it is not appropriate golden model. And finally, as I already mentioned, it is when to stop simulating. So during all these traditional approaches, we see different we go through different techniques. It is widely used validation techniques. There are lots of commercial tools that are working with emulation of different inputs, and especially it is FPGA-based hardware emulators. There are many automatic tools for bench creation. I mentioned here as some of them. It is Specma, Vera. They come from. They are being developed in house, but it is they are. Serve to special needs, and sometimes we need something more general, something more reliable than just considering all the possible inputs. Following this approach, we can detect some of the bugs on very late stages of development, and sometimes even we detect issues when product is already ready to go into the market, but it comes out that the problem is not a coding issue. It is not an issue that was introduced by a developer who coded some specification. It is design issue, and some of them, sometimes it appears that some of the features are neglected, and there is no interconnection between those between different parts of the product. And considering separate functions of the product and testing all possible inputs for each separated functionality doesn't cover all the relations, all the ties in the product, and doesn't guarantee safety of the system. What is alternative? It is formal methods used in software verification. How many of you ever used some formal methods? Okay, not much of you. What is a formal method? First of all, I will tell that formal methods is approach that is based on mathematical concept. It is it's based on mathematical notations. It is a specific language. We use specific language. It is strictly formal language, and everything in those languages can be can be done only using some specific argumentation. So whenever we do create specifications using natural language, we say this, and this, and finally something is clear that it follows from above mentioned points. But in case of it is possible that, in fact, when we say it is simply follows from our facts, it cannot follow from the fact, and it is just our imagination that it is follows, and we missed something in the chain, in the logical deduction. But in case of use of formal tools, formal methods, every step is performed using the specific rules based on some symbolic language. And formal methods provide a more rigorous approach, and using formal methods, we can easily detect issues in the software on early stages of development. It is we do not need to wait for the system to be implemented on some programming language and then start testing it and simulating the system, giving all the input values. Using formal methods, we think about the verification on early stages, as soon as the design is started. So formal methods can be complementary to traditional techniques, but being a complementary to traditional testing, it can serve separately and entirely. Using only formal methods, we can prove the system correctness, and in opposite to traditional testing methods, we can not only say that tested system behavior on 1 million inputs, and there are a couple of inputs that we didn't know what will happen, and just judge about them on some probability mechanism. But in this case, we can say that we prove the system correctness. Talking about proving system correctness, we are talking about some mathematical models, mathematical theorems that are proved using specific languages, formal languages, and there is no space for ambiguity. So formal verification we can divide into three-step process. It is formal specifications, it is formal models, and verification itself. And let's talk about each of these processes more deeper. As I already mentioned, when we provide specification, it is just usually it is done using high-level languages. In case of using formal specification, we can nowadays there are different tools based on specific languages. I just mentioned the system, Z system, which is based on set theory, which is formal set theory, and you can deal with it, use it to formalize all the specifications. And system requirements and invariable constraints are modeled using that language. And what is the logic of which that is undergo all this approach? We on different problems, depending on the area where you are, where the software is being developed. There is sense to switch between different logics. The simplest one is propositional logic. A more advanced approach is first-order logic, but based on the first-order logic, sometimes it is not depending on the systems. If it is reactive system, real-time systems, just only using traditional classical first-order logic isn't enough to say to judge system about system behavior, and we need to use some specific logics. It is temporal logic or some other logics that are being developed by logicians, mathematicians, or computer scientists, and each of these logic can be considered as targeted for a specific purpose. Another approach is automata approach. It is there are labeled transition systems or Bookio automatas that are can be extensively used in formal specifications, and all these we can use either of these tools separately or combination of those tools to provide deal with to provide formal method in specification verification phase. The other, the second step in this process, it is formal models and how we create those models. It is again with creating those models. We think about the system. It can be we need to think about concurrency issues and how to model all those concurrencies on the in our model, how to see system behaviors on the formal model. And here again, different languages can be used, and transition systems also is of the help to resolve this step. And final, last but not least, is a verification in this process. It is we check that on verification using I'm already talking about formal verification, not traditional verification process. We are checking that model satisfies specification that and to make this check, we can use different approaches. It is semi-automatic or fully automatic, and there are each of them has its advantages and disadvantages. Here I bring some very simple, maybe trivial example to use some techniques from formal verification. It is here I bring into formal verification space also designed by contracts, where you deal with precondition and post conditions. So talking about precondition, talking about contracts, we deal with them as assertions, but it is in contrast to assertions, it is more powerful as it provides more options in regards to object-oriented systems. So precondition means that precondition true before the statement is executed. Postcondition is true when must be true when something is performed and it is as expected. It is performed as it was expected. So in case of this greater common denominator calculation, it is we consider two positive numbers, and we expect that each of them will be positive and have some value, and after calculation x and y, GCD of x and y will be equal to GCD of a and b. So using formal verification, we can formal verification technique. We can talk about precise statements, and we do not need to keep additional information in our minds. Everything that we are deal with should be formalized in system. It is in case of contract by design, it is in the code itself. In case of using other systems, it is just included in the listing of the programs of special of that tools. So it is we need precise description of design, and it can be done again manually or in a semi-automatic way. And when we can say that formal verification fails, and when we succeeded in verification of the system. The system verification can fail in case there is an ambiguity in the design of the system. Maybe the system is designed not properly. It is too abstract to judge about some concepts, to think about something specific in the system, and it doesn't provide. It cannot operate with some concepts, even because it is too abstract. But Another thing is when everything is in design seems to be okay, but it fails because there is a contradiction in the specifications. Because what is a specification? It is a list of assumptions, list of formulas in some specific language, where you deal about some where you state about the properties of the system and about the possible inputs, and expected output isn't the logical consequence of the input of the given input and system specification. But in this case, it is we detected a hole in the design, and it needs to be fixed immediately before going to the next stage in the development process. In a if verification succeeds, it doesn't yet mean that everything is okay. Maybe again the specification is trivial, and everything. It doesn't mean that everything is okay, because maybe there are many things that can be removed from the specifications, but the system will behave in the way it behaves now. But if design meets the specification, then you are succeeded in your approach, and you can switch to the next step in your development process, and we can start implementing the code for the designed features. So, talking about all these specific languages, talking about mathematical models, usually talking about mathematics, it frightens most of the development society. We used to think about development process as a coding, but development itself isn't a coding, and it is not just a dull translation from one language into another. It is, in fact, specific. It is real and deep development is a serious responsibility, and it is we need to be very we need to have a really deep look into the problem, problem area where we are trying to provide a high-level code before just translating given specifications into some Java code, C++ code, or any other code that is expected to be given. So we need to think about mathematics, but here one question arises. So it is additional headache having some mathematical knowledge, and formal verification just complicates the development process. No, in fact, it doesn't complicate the development process, because you will think about quality of life, as it was mentioned in the one of the first slides. Computational systems quality is quality of life, and if we want to think about the quality of life, we need to pay the price. Knowledge of some specific languages, some formal languages, and some cooperation, maybe science and engineering cooperation, is the price for the high quality code. So verification, formal verification techniques can be, I just mentioned here 3 major techniques that are used in formal verification. It is equivalence checking, that is mostly used in hardware verification process. It is model checking and theorem proving. The last one used both on hardware and software for verification, both and hardware and software systems. While the first one is mostly used, I cannot say it is entirely used only for hardware systems equivalence, but mostly used for hardware in hardware a sphere. Equivalence checking. When we talk about equivalence, it is a question whether two given circuits are equivalent or not. And it is known that the circuits, the equivalence is a really tricky question. Equivalence verification is a really tricky and computationally hard problem. But sorry, it is useful for optimization validation. It is it can be used to scan chain intersections. It is there are lots of instruments. There are lots of tools that are developed by different companies for their specific to meet their specific needs. And one of the giants in this sphere, Synopsys, has different tools to. It is commercial tools, not just only internally used tools for equivalence checking. During model checking, it is another technique in formal verification. It is, in fact, it is fully automated because you do not deal with different parts of the system. You consider the system's behavior as one general one, as a whole, and it is the question if the system, if the model behaves as it is expected. And to answer those questions, there are again two different tools. It is spin formal check. They come mostly from academia, but it is not only academy that works in this sphere. It is also transferred into the industry. It is there are tools from IBM, Intel, and different giants of the IT industry. Last but not least, and I would say the one that we used to prove to detect some issues in one of the products we are working on in VMware. It is theorem proving technique. It is one of the most powerful techniques, but it needs again really expertise knowledge, either domain and knowledge of mathematical formal systems, formal languages, because to be able to use theorem provers to detect some issues, to detect some problems in your software, in your system, you need first of all formalize your system's behavior. And to formalize system behavior, you need to have be expert of the product you are considering, and you have to be well trained in the sphere of formal systems. So here again, there are lots of theorem provers. Most of them which are open source. It is they are coming from academia. It is SPAS, PVS, HOL. There are many other tools, Vampire, Matita, and so on and so on. And part of them are fully automated. Part of them are semi-automated. In case of semi-automated, as I mentioned, there are advantages in each of them has disadvantages and advantages, and You might want to use a semi-automated tool when you want to immediately make some changes in your design, in your specifications, and see whether it fulfills your changes fulfill the gap. As soon as the problem is detected using semi-automated tool, semi-automated theorem prover, you can backtrack, make change, and run this prover again to see whether the problem is resolved or not. In case of fully automated provers, you just everything you have, you give as an input, and and expected output is also given as a formula in some specific language, and it is most of the systems and the fastest implemented systems work on trying to find the contradictions in the set of formulas. Here I consider just a primitive example to give a quick overview how we deal with these theorem provers. It is a library exchange formalization. So I consider from the university course, logic course, we know that proposition is something, is a statement that can be either true or false. And here we consider four statements, S, R, L, and Q. And S is true when the book is in the stacks, R when the book is on reserve, L the book is on the loan, and Q the book is requested. So usually we can say that how the library operates, how the library works. If the book is on the stack, it means that it is not on reserve or it is not on loan. The first assumption. The first one. And the second one is if the book is on reserve, it means that it is not on a stack or it is not on loan. And similarly, the third one. So it is assumptions that can be considered as an axioms when we deal with when we think about library functionality. And what is the second assumption? It is the book can be requested if it is on stake or it is on reserve. So the question is whether if the book is on the loan, whether it can be requested or not. In fact, I claim that if the book is on loan, it's not true that it can be requested. Usually, it is the proper behavior of the. It's a normal way of dealing with of library operation, and I do not bring all the complicated syntaxes of any theorem prover. I just assure you that you can using these assumptions and adding this question to the assumption list, see that the system is not contradictory, and if the book is on loan, it cannot be requested. But if we remove one of these first three assumptions, we will come to the contradictions, because it wouldn't be possible to properly say that we can deduce that L implies not Q. So this is just an example, and how the theorem provers work. And to formalize the system, you need to understand how the system functions, and you need to represent it in some logical language. Formal verification can be very useful in case of small control-intensive designs, blocks of hundreds of latches and state bits, and it provides it guarantees the system that system is free of bugs, and it doesn't need any additional steps in simulating systems behavior. We do not need to run everything, all possible inputs. We just prove that the system doesn't have anything wrong in itself. There are several systems examples that are coming from industry, and again, this is from the industry giants. It is from IBM, from Intel. There are formal verification tools being developed in Microsoft. Even for Azure, they are using some provers, and they developed their own provers to prove the system's behavior. What are the challenges in formal verification? Yes, it is more complex. You need, because you need to spend more time on different stages of different stages of development process, and it is again in case of dealing with different formalization. Formalization itself isn't a simple task, and during the formalization you need to be special attention need to be given to assumptions, axioms lists that you put into the system's behavior. This is mostly what I wanted to deliver. Thank you for your time, and if you have questions, I would be glad to answer them.
Hi, I have a question. So you say that the formal system cannot be wrong, it's bug-free, 0 bugs. Pretty much that doesn't make sense to me, but given that this can be true, what happens when this formal system interacts with a non-formal system? I believe that makes this system not bug-free.
You mean interaction of two formal systems?
Two systems as like in the real world.
If either of your system is not contradictory and sound and consistent, there is no major issues in dealing in interaction of two formal systems. So if you formalized one system, for example, it is once you modeled one system, software using one language, and there is another software that reused this one, and you can give your input from a formal input from this from first one to the second one. There is no major issues, and it is just a transition from one formal language to another formal language. And nowadays there are standard libraries that use some translation techniques between those provers, and as on the level of the automata, you need to think about the models, how to union those models by yourself.
Can you actually say that every system can be, tested with a formal method, or proven to be, bug-free?
Sorry?
Like, can you say that every system can actually be tested with such a method, with the application of such a method?
Yeah, nowadays using classical logic, and especially when you switch to intuitionistic logic, and which is considered as a constructive logic, almost everything I would say, I tend to say everything can be modeled. The only question, how much effort you will spend to model it. That's why I mentioned that along with the classical logic, we have different kinds of logic being developed. It is temporal logic, concurrent logics. It is different logical systems that you invent, implement to meet specific requirements from the systems software industry.
Thank you.
Okay, thank you for your attention.